Okay, so I have just 1 hour to really present you a complete morass of things. So I'm going to do my best, but I'm actually not going to use my tablet today and write equations. I will start by spending maybe 5 minutes, 10 minutes, just discussing, referring to the notes that you have, the last aspects of the algebraic beta-ansatz that you minimally need to understand what's coming thereafter. Afterwards, it's just going to be just a Beamer presentation, so it's kind of appropriate for an end of day, sunny afternoon, thing to wrap this up. My objective is really to bring you up to date with current happenings in condensed matter as far as integrability is concerned. Maybe even some of you might find some inspiration for future work in there, because there's really, certainly the things that I'm going to talk about right at the end are things that are not even in journals yet. So they're on the archive, but they're not published yet. And I think they point to many possible developments for the coming years. Okay, so last time we kind of rushed through the basic notions of the algebraic beta-ansatz. In fact, I kind of skimmed through the most important parts there. I told you that we could pluck the Heisenberg Hamiltonian out of thin air by making, at each step of the construction that I was proposing last time, the very simplest choice for the R matrix, and then for the monodromy matrix out of like local 2x2 matrices, these L operators that you get and things. But I kind of didn't go through the details. So I don't know if all of you, some of you, or none of you actually went through the notes. Did anybody take the time to read the kind of plucking of XXX out of thin air? It's kind of better things to do last night. Okay. So, well then, with this statement, let's just let me just very briefly summarize what we have. Okay, so again, I'm using this just to accelerate. I don't know if you can read, but certainly I'll give you the equation numbers from the notes that you have. So the idea, you remember, was just to construct sets of commuting charges out of thin air. This led us to the introduction of an auxiliary space, the realization that these monodromy matrices could be used to construct transfer matrices, the fact that these monodromy matrices are intertwined by some object, which we ended up calling the R matrix. This R matrix having to satisfy some compatibility condition, which is the Yang-Baxter relation. And then essentially from that point onwards, it was really a question of finding representations of these algebraic structures. At the end, last time, I proposed to you the very simplest non-trivial form of an R matrix, which was this R matrix with the two off-diagonal terms, the 1BCCB1 4x4 matrix, the minimal size that we have for something non-trivial. And then at the end also, I told you that when we want to realize or find a representation of the relation RTT is equal to TTR, we can simplify our lives by taking T to be like R. Okay, so this is essentially the construction of these fundamental spin models that I was referring to. So the idea is that we introduce some local Hilbert space on side J, and then we say that on this side J, I'm going to take some kind of operator here and identify it with the R matrix, maybe with some inhomogeneity here. You can read the details about that in the notes. Now, the point of constructing a lattice model out of this construction is to take tensor products of local Hilbert spaces. So here in this case, I'm going to build an n-site chain out of these things. And I will consider realizing my monodromy matrix as a product of these operators on each site. Okay, and that's essentially where the magic occurs. Because we can just use the Yang-Baxter relation RRR is RRR to show that RTT is equal to TTR, and therefore that the trace of this object in auxiliary space is going to give us a full-fledged transfer matrix from which we can use these identities to generate all our conserved channels. Okay, so just to run you through what you will learn from the notes, when you will read them eventually. You go through this, and then using the explicit form of the R matrix that we chose essentially allows you to realize this monodromy matrix, and therefore this transfer matrix. Then essentially the magic thing is that if you choose your parameters right, what you observe is that you can simplify all of these to permutation operators, products of permutation operators, and then suddenly, when you write down the equation, you remember the very first equation I wrote down in the algebraic beta ansatz thing was how to use this generating function, this generating operator that we had to construct the charges. So this is just what is happening here. We're just using the transfer matrix, calculating its first derivative here, and using the fact that this is going to be a conserved charge. Okay? Such relations are called trace identities. A trace identity is essentially how you relate a conserved charge to various derivatives, including higher derivatives, of course, of the transfer matrix. Now the magic thing in this construction here is that you see you can do this thing explicitly, and then you just get that this charge here is a summation over permutation operators between the spaces on adjacent sites. But of course this is a simple operator to write down in terms of Pauli matrices. Okay, so the operator that you obtain here is just essentially the XXX Hamiltonian. So you can just do the algebra and notice that the first conserved charge that you naturally construct out of this is simply an S dot S nearest neighbor interaction on a lattice. Okay, so it's just precisely the XXX chain. Okay, so that is the statement that is made. I invite you to reproduce all the details from the notes to see explicitly where it comes from, but it gives you the idea of where it goes. And once again, we did not do anything but the simplest choices at each level, and we plucked XXX out of thin air. Okay? That's really the idea here. So then you can go on with the same construction and consider more complicated local Hilbert spaces and things like that, and see what you get. Okay? And try to reproduce all the integrable models you know from this kind of construction. Okay? So are there questions about this? I mean, I know it's probably all mysterious if you haven't done it yet, but that's the general idea. Okay? Now, why is this in a sense useful? Because quite frankly, we haven't done anything that we can't do with beta ansatz here. Essentially, you'll find, so these are all the kind of final conventions for XXX in the most handy way. You'll find them in the notes, equations 1182 to 1189. Okay? So why does the algebraic beta ansatz add anything to the coordinate beta ansatz? After all, we already know the Hamiltonian that we diagonalize with coordinate beta ansatz. We know its energies, the energies of its eigenstates, the beta equations, and things like that, and that's the only thing that we have here. Well, the reason is that, in fact, this algebraic structure allows us to go much further quite easily. One of the first things that, so here it's just an XXZ case, let me just jump over this. There are some properties of these objects that are relatively straightforward to calculate. So first of all, there's an incredibly important theorem in the algebraic beta ansatz. So this is known as Slavnov's theorem, Slavnov's formula. The idea is that, as we've seen, we now construct states out of products of these B operators acting on the reference state. So essentially, all quantum mechanical questions that we might want to ask can be expressed in terms of, if you want, overlaps or matrix elements of these ABCD operators, the entries of the monodromy matrix. Now, Slavnov's formula gives an explicit formula for such an overlap here. So say this state here is characterized by rapidities that solve beta equations. And this state here is given in terms of arbitrary parameters mu. Slavnov's formula calculates this in the form of a determinant of a matrix whose entries are explicit meromorphic functions of the spectral parameters of the Bragg-Ket states. Okay, this really kind of comes out of the blue, but you see how you derive this essentially. So we know the commutation relations between D and C. They're given by the quadratic algebra that we had before. Unfortunately, this seems to be dying. Do you have another laser? Oh, I think it woke up again. Yeah, okay, good. Let me see if I, well, keep it there now. Okay, so remember, this is really a beta wave function. Okay? It's a factorially large number of terms when you write it down in real space. Now, in the algebraic formulation, this is much simpler because it's a product of some operators acting on some reference state. But these operators, they commute with each other. Okay? So it's a very, very simple algebraic representation of the wave function. And when you calculate such an overlap here, if you were to calculate it using the coordinate beta ansatz, you would once again have to do a many-fold spatial integral of sums of permutations over both sets. So it's just a complete disaster. And the magic, of course, is that these whole sets of things, they add up to just some determinant. Now, you might not know this, but of course you can write a determinant in terms of a factorially large sum if you so wish. However, if you need to evaluate a determinant of a matrix of size m, then the operational count is only n cubed. Okay? So you've transformed something which is exponentially complicated in system size to something which is polynomial in system size. This is extremely economical. And in fact, all the results that I'm going to present you today are based on this fact that the algebraic beta ansatz allows to control all these combinatorial sums to distill them into these extremely efficient expressions. Okay, that's the magic of the beta ansatz here. So that's Slavnov's theorem. I'm not going to prove it, I'm just going to tell you it exists. And then, so you'll see in the notes, it's going to be precisely stated with things. Now, the other crucial element is that, of course, the physical questions that you want to ask are formulated in terms of local spin operators when you're talking about a spin chain. So, if you have experimentalist friends, then they will ask you, well, okay, so I need to know how flipping a spin on a certain site on a certain time is going to affect the value of the magnetization on a different site at a later time. That's what I want to know. Okay, so how do you formulate that? You formulate that in terms of a correlation function between spins, a space-time dependent correlation function between local spins. But of course, the problem with the algebraic beta ansatz is that it's based on these A, B, C, D operators, which are utterly non-local in terms of the local spin operators. It's very complicated. So you need to be able to translate one language into the other. And that was essentially the stumbling block for about 10 years in the algebraic beta ansatz until Jean-Michel Maillet and his group in Lyon found the solution to this, at least for the spin chains. And in fact, the solution to this is quite funny because it was derived by Maillet et al. Using the F-basis, which is a huge construction, dozens of pages of calculations, but then later on you realize that actually you can find a proof of this that fits literally on a postage stamp. Rather large postage stamp, but still, if you go to Liberia or something, they have these large postage stamps, so you can fit it on. So the idea of the so-called quantum inverse problem is precisely to implement the mapping between these local spin operators and the ABCD operators appearing in your monodromy matrix. And the way it goes, again, is completely trivial because what you have essentially is your R matrix here, which becomes the L operator whose product is the monodromy matrix. And then you can look at this and evaluate it at a specific point of the spectral parameter. And then when you write it in Hilbert space, so essentially here these elements here are all Hilbert space elements. So the 2x2 structure is auxiliary. Then you can immediately identify local spin operators with various combinations of A, B, C, D, with some operator here, which is just a lattice translation operator. So then you end up with this wonderful equation here, where on the left-hand side, you have local spin operators. So sigma, whichever component of site J, is written now as an utterly non-local product of these A, B, C, D operators. These are very simple operators. SU2 algebra, you might think that computations are easier with the representation on the left-hand side. Actually, in beta ansatz, the computation with the right-hand side is much easier. Despite the fact that these ABCD have this quadratic algebra, you can actually control the calculation of the expectation value of such products between eigenstates. Okay, so that is the magic. The combination of the solution of the inverse problem with Slavnov's theorem means that you get explicit matrix elements for physical local spin operators in the basis of beta eigenstates. Okay? Absolutely crucial step in here. So, yes?
What does it say?
It's a so-called inhomogeneity parameter. So in the so typically what you can do is construct a completely arbitrary chain where on each side you have a given shift of the spectral parameter. Just you can't do that. You can assume that it goes to a limit where it's the same on each side, and then you see in the conventions that I have in the notes, I tell you which value of psi you need to take depending on what your value of the anisotropy is, and then to construct the xxx or the xxz. Okay, so it's just some parameter that you can fix at your convenience at some point. Okay, but that's essentially the logic. So you combine the solution of the inverse problem with Slavnov's theorem, and this gives you the matrix elements of the physical operators you're interested in the basis of the exact eigenstates of the theory. Okay, so you can't do that for any other many-body problem. It's really a kind of unique occurrence in physics. Okay, now in the end of the notes you see the explicit realization of this. So now essentially what I want to calculate is, say, some spin operator here where these states will now be beta eigenstates. And then you just go through it and you find once again that these matrix elements are typically just some determinant of some known matrix. Okay, so some matrix, you find all of that in the notes. Okay, you can look at the details by yourselves. But the main point is that this algebraic beta ansatz framework has allowed to completely control all these, in principle, factorially large sums and overlaps and things, and distill them into something which is brutally efficient. Okay? So that's the kind of miracle of it. Any questions about this? Just to have a bit of reading for the weekend, but then you won't get a weekend from your organizers anyway, so maybe you'll read that the week after the school, I don't know. So. Okay, so let me now just shift to the other part where I'm going to show you how this is used. Okay. So yesterday Matthias was asking me questions. I just wanted to flash a couple of fun things. So this first article of Heisenberg in 1928, and then 1930, Bloch essentially does an approximation where he drops these phases, like I said, and then gets the wrong number of eigenstates. And then Bethe publishes the first paper in a series where he essentially constructs the correct number of solutions, and then in future work, article 2 and things, generalization to higher dimensions. There you have it. Anyway, it's quite interesting historically to see how that happened. I guess in those days refereeing was a bit different, so I wonder how far he actually did this. Maybe he was just still young and very self-confident, and he thought he could do it. But I don't know if he tried actually. So probably hadn't. Anyway. Okay, so the applications of integrability in many-body physics, essentially, they've manifested themselves in very many different settings. I of course, don't have the time to really describe absolutely everything for you, but today I'll just concentrate on quantum magnetism and a bit of ultra-cold atoms as well. But there are other situations, for example, quantum dots, NV centers, that are used these days for essentially quantum information processing. You can also approach that with integrable models. And even if you go back to the glory days of nuclear physics, essentially some of the models that we know that are exactly solvable were originally written in the context of nuclear physics. So I think that it's probably a kind of way back from integrability into nuclear theory in the future. Now, okay, so the two models that I'll discuss here, you've already seen, okay, the ones that I included in the notes. And I just want to show you essentially two different things. Actually, maybe just a little word. You will know that Gaudin is one of the big, how can I say, kind of big wise men on top of the mountain for integrability. So he had this really great book in French that was published in 1983. It was actually translated in Russian in 1989, but it stayed in French for quite a while. So actually, at one point, I wanted my students to read it. So either my students would learn French, or I would translate it in English. And then I thought it was easier to translate it in English. So this is now available. And despite being 30 years old, I think one of the points is that you can see by looking at that how advanced Godin's knowledge of these things was at the time. So if you have time, you can look at this. Okay, so what do we do? Essentially, me and my whole gang in Amsterdam, we always more or less play the same game. What we do is that we formulate an interesting physical problem in the language of beta eigenstates. So here I might be looking at a certain system in its ground state. I might be looking at the system at a certain temperature. I might be looking at a prepared state in various circumstances. And then I'm going to do something to it. So maybe I'm going to measure something or whatever, try to time evolve it according to a different Hamiltonian, whatnot. And then I just do essentially what you learned how to do in your second, possibly even your first course in quantum mechanics. You just calculate everything in terms of these exact eigenstates, where you represent all these operators as matrices in the basis of these exact eigenstates. Okay, so it's really, there is absolutely nothing philosophically challenging once you've accepted the first few postulates of quantum mechanics. This is all that we do. We apply that in complicated settings. Okay, so for example, when we actually calculate correlation functions, well, maybe I can just very briefly show you a couple of equations that you have in the notes to set the notations. Okay, so for example, one of the things that we might want to calculate is the correlation function between spins on the Heisenberg chain that are sitting at sites j and j prime with a time difference of t between them. Okay? Now the way we calculate these things here is of course to use a so-called Lehmann representation. So what you do is that you take this product here and you insert a resolution of the identity here between the two operators. So you do a full summation over possible intermediate states here. Again, this thing is dying. It's kind of dying and resuscitating at the same time. It's interesting. So you introduce a resolution of the identity here. And then, essentially, what you can do is perform these summations. The integral over time just gives you a delta function in energy. And then you just get momentum conservation here. So you get the momentum component of the operator between the ground state and the intermediate state here. And then you get such sums here. Okay, so I guess you're familiar with these kinds of things, right? Lehmann representation? Yeah. Okay. Okay, so essentially I'm just going to treat this Lehmann representation. That's where I was in the presentation. Now, of course, what interests us is to calculate these things exactly as far as possible. So we need the exact basis of eigenstates. So this, as we've seen, you get from beta ansatz. I'm not going to talk about quantum groups at all today. The second element I just showed you, or I just kind of argued for you that the algebraic beta ansatz was able to offer them. And now, of course, the very complicated stuff is to perform the actual summation over intermediate states. Okay, so this is where the remaining challenges lie, if you want, at least for the models I'm talking about. Of course, the problem here is that the summation over intermediate states runs over, in principle, the full Hilbert space. So you're really talking about an exponentially large number of states. But that's just computationally too much. You wouldn't be able to do it for a thermodynamically large system, except in very special circumstances. Again, I'm not going to talk about it today. But typically, the thing that occurs is that most of the states in Hilbert space are actually utterly irrelevant for the things you're interested in. So these correlations between spins or between atoms, they are carried by a very, very small subset of states in Hilbert space. So if you know where to find those, you can focus all your computational resources on those to obtain your correlations to very, very high accuracy. Okay, so that's, I'll just show you some examples of that. Okay, so the idea of navigating the Hilbert space, well, you understand how that goes. Essentially, you label all your states with the quantum numbers, you solve the beta equations for the rapidities, and then essentially you see that it generates for you all the states. You see how this very, very quickly becomes impracticably large. So you just have the type 1, type 2 modes, for example, for Lieb-Liniger, and then you get these backflows of the positions of the rapidity. So you need to solve these things as best you can. And then, so just to summarize the approach for the correlations, what you do is that you just use your beta ansatz to get the conditions for the eigenstates, so the beta equations. You get your resolution of the identity from all the solutions to this. You use the algebraic beta ansatz to essentially compute the matrix elements of the physical operators you're interested in, and then you just sum up. Okay, and that's just call this algorithm I built up abacus, because it's like playing with an abacus, just complicated abacus. And then you end up with such things that I'll talk about in the next little while. Okay, so there are many, many cases where we've been able to do this, because of course, like I said before, the monkey trick that you learn how to apply to one model, typically you can apply to other integrable models. So I'll just very briefly show you some things about Heisenberg, about XXZ, and about Lieb-Liniger. Okay, not in that order. Okay, so let's just talk about the physics of the Lieb-Liniger model. So here I am looking at density-density correlations in the ground state of the repulsive Lieb-Liniger model. Here these computations are done for 200 particles. So it's not thermodynamic, but it's big enough. In fact, there are more particles in the calculation here than in the experiments that I'll show you in the one. I'm sorry? Okay, so let me just specify this a bit. So gamma is essentially the interaction in the notations that you have in the notes. Gamma is equal to the interaction parameter C divided by the particle density per unit length. Okay? So if you're at unit filling, gamma is equal to C. Where C is really, remember the thing multiplying the delta function. Okay, so if you have a very, very high value of gamma, then essentially the system looks very much like a system of free fermions as far as the density-density correlations are concerned. At low gamma, it looks much more like a gas of free bosons, except of course it's non-trivially modified. Okay, again, so these correlations are obtained by brute force summations of these things using the beta ansatz. Okay? So how do you understand such things? Oh, by the way, I guess I should tell you this. In these plots here, the horizontal axis is momentum, the vertical axis is energy, and of course the color coding is just the size of the correlation. So if you were to do a scattering experiment on such a system, this is essentially the observable that the experimentalists would come up with. Okay, where essentially the color scheme would be essentially the number of excitations they found at this this k and omega point. Okay, so by looking at such pictures of correlations, you really can understand quite a lot about the physics of these models. So we've talked about the type 1 modes. So the type 1 modes are the ones that mark the boundary of this single particle Hall continuum here. The type 2 modes, they're the ones living at the bottom here, marking the threshold at the lower frequency. And then you see you've got some low energy modes occurring with these, like calling them the Umklapp excitations, where you just take one particle from one side of the Fermi sea and you bring it to the other. Okay, so these are the gapless points you would obtain if you were to bosonize this here. Okay, so for example, you can see calculation of an impossible to perform experiment where you measure the density response function as a function of all k and all omega as you crank up the interaction. Okay, so the important thing is that in here, besides the fact that it's a finite size calculation and that you don't sum over all states in the Hilbert space, the calculation is up to that exact. You can verify the accuracy of the calculation by computing so-called sum rules. So these correlations have to obey certain identities, And essentially you can quantify the accuracy of your calculation by looking at the saturation of these sum rules. So you can tell, for example, that this correlation at a certain value of the energy is going to be 99.5% accurate. Okay? So you can quantify all these things. Sum rules are discussed in the notes I gave you. So just very, very briefly, I just want to tell you that one of the important things about these one-dimensional Bose gases. Yes, question?
Well, why is this gaseous excitation sits in the middle of the Fermi
zone? So the 2kF mode here is here, right? It's completely on the other side.
Oh, I see. But why is it? Why is it k equals 2kF?
Because essentially, so if you
okay, so because there's the width of the zone.
Exactly. So you're in 1D. You're in 1D. So the Fermi C itself has a length total of 2kF, right? Because it goes from minus kF to plus kF. Okay. Yeah, let me just check through this. Okay, so one of the things which I want to show you are some experimental realizations of these models. There's much more to say about quantum magnets, but there's some very recent stuff about 1D Bose gases that I want to tell you about. You might or might not be familiar with the field of cold atoms. So cold atoms, for example, in optical lattices. So this is a field that's been emerging for the last almost 20 years now. Whereby essentially experimentalists are able to use light fields, so laser beams, in order to create artificial potentials in space for trapping atoms. Right? So what you can do is just create a standing wave of light, and then of course there is a coupling between atoms and light, which is very, very weak. But if your atoms are very, very cold, they will get trapped by the light onto various geometries that you can choose to be 3-dimensional crystals, 2-dimensional crystals, or 1-dimensional tubes. So there are experiments that are being performed where you take two counter-propagating pairs of laser beams and you create a tube-like potential in which you can put very cold atoms, typically rubidium is used, and then the effective theory for these atoms, which propagate on one line, is the Lieb-Liniger model. Okay, so they really realize the Lieb-Liniger model. The problem is that they create a Lieb-Liniger model which inherently sits at a finite temperature. It's very difficult to go to the ground state. So doing calculations at finite temperature for the correlations, it was quite a challenge, but we got some results on this with one of my ex-PhD students. So these are unpublished results. They're on the archive, but they're not free reports. They're not in published papers yet, showing the correspondence between the experimental observation using a method known as Bragg spectroscopy for the density-density correlations in these gases as a function of energy and momentum compared to the calculations. Okay, so you might not be used to experimental fits of theoretical fits of experimental data and things, so maybe later you'll be more impressed. Anyways, so this is something which you might hear more of in the future. Okay, so the important thing is that the existence of an exact solution for the Lieb-Liniger model here empowers you to perform computations of these correlations that you cannot do with other approximate schemes. Right? So you really see the effects of the interactions and of the temperature, and you can control them because your calculation is based on beta ansatz. Okay. So, have you ever heard of cold atoms and things? I guess you all. Okay, so maybe let me jump through this. This is just how to interpret the data in terms of these type 1 and type 2 modes. Okay, so for spin chains, in fact, I think things are much more, if you want, under control, at least for the experimental correspondence. So this is the calculation from a little while back of the dynamical spin-spin correlation, again as function of momentum and energy, for a chain which has 600 sites. Okay, the saturation of the sum rule for this is 99.1%. I know that at most there's a fraction of a percent missing somewhere, but that doesn't matter for the experiment because the accuracies are more of the order of 5%. Okay, so you remember we talked about spin-ons. Okay, I told you, I showed you the dispersion relation of spin-ons. Well, essentially this is the line corresponding to the dispersion relation of spin-ons, and this is the two spin-on continuum. The correlation is non-zero here, but it's stupidly small. And the correlation is identically zero here due to kinematic constraints. Okay, so you see it's an antiferromagnet because the spins, they like to have a response at momentum pi, right? So it just goes up, down, up, down, up, down. Okay, but it's accompanied by this little critical line here, and you've got critical scaling associated with this. Okay, so this is what you get out of integrability. And the nice thing, of course, is that integrability allows you to quantify the correlation irrespective of where you sit in energy. There's no approximation like you do when you do a CFT approximation, when you do some post-nization or things like that. Then you get the response only at this point and at this point. This one is well symmetry. Okay, but you fail to get the response in these regions here. So beta ansatz is able to move here without any problem because, of course, when you write a beta ansatz wave function, it's an exact wave function, irrespective of whether its energy is that of the ground state or if its energy is, you know, sky high in the Hilbert space. Okay, so that's the important aspect of it. So then you can study many things. For example, here these are the zero field correlations for XXZ chains at different values of the anisotropy, and then you can characterize how the correlation weight shifts from one place to the other as you crank up the anisotropy, and then you get back to the XXX point. Okay, so this is just to show you how much physics we can get out of that. You can also just have fun and do computations of the correlations as a function of magnetic field, and then of course the excitations that you get become very complicated. So that's just the kind of thing that you can in principle compute. And now let's just talk a little bit about what use this has. Okay, so the method that is being used to investigate quantum magnets is called neutron scattering, like inelastic neutron scattering. So the idea of that is completely trivial in a sense. What you do is that you throw some neutrons towards your crystal, and neutrons, of course, have only a magnetic moment that can interact with the crystal, so it will interact with the local magnetic moments in your insulator, and then it can induce some localized spin excitations. And these localized excitations, in this case here, it's like an antiferromagnet that gets excited by a neutron. These excitations under unitary time evolution will start propagating. Okay, so the spin-ons that you have in these chains, to a good degree of approximation, they're like domain walls marking the transition between two different types of Néel ordering, either up-down or down-up. Okay? But you see why you only have pairs of spin-ons appearing, because if I flip one spin, I create two domain walls. Okay? Or 4, or 6, but not 5. Okay? So that's why spin-ons appear only in pairs in these magnets. And now the implementation of this, of course, so this is like the same cartoon. So the implementation of this is non-trivial. So here's a kind of sketch of an experimental setup. The kind of old-fashioned way of doing it was to have a nuclear reactor, okay, producing a thermal flux of neutrons, and then you would dig a hole in the reactor so that neutrons would come out in one direction. So that gives you at least directional control. And then you want to have the speed of the neutrons controlled. So how do you do that? You use so-called choppers. Okay, so this sounds really high-tech, but the idea is that you have two sets of doors, and if you want slow neutrons, what you do is that you open one door, you wait, then you open the other door, and you close it. If you want to have fast neutrons, you do, if you want to have faster neutrons, you do this. Okay? It's as simple as that. So you get a focused beam of neutrons with a sharp distribution of velocities hitting your target. Okay? So you have the target somewhere in the middle, and then all around you have like a half dome of detectors. Each detector will essentially click when a neutron hits it. And of course you know where the detector is, so you know essentially the angle of deflection that the neutrons incur. And also you record the time at which the neutron arrives. Therefore, you know at what speed the neutron went as it emerged from the sample. Therefore, you know how much energy it deposited, so how much kinetic energy it lost. Okay? From the directional dependence, you can recover the momentum and the frequency dependence of the response function. Okay? It's as simple as that. Of course, the implementation of this requires an apparatus which is multi-billion dollar. Okay? And of course, these things were not built to study one-dimensional quantum antiferromagnets. These things have extremely important industrial applications, of course. Neutron sources used to assess essentially the quality of materials, to investigate structures, and, magnetic structures, and very many things. So essentially, this type of physics is really done when the physicists get bored of working for these things. They want to do some interesting physics. So then they say, oh, you know, let's look at quantum critical antiferromagnets in one dimension. Okay, so it's kind of a luxury to have that. Okay, so essentially this is something, so neutron scattering is an old technology, right? So a few years ago there was a Nobel Prize that was given about this. They had to dig these old researchers out of the closet in which they had been hiding for 50 years and thought, oh, okay, it's your turn to have the Nobel. But so it's been around for many, many decades. And essentially what's been happening in the last few years is that there have been better and better measurements of the neutron scattering response function of crystals that are extremely good realizations of Heisenberg models, spin-half Heisenberg. Okay, so I'll just show you a couple of those today. The most recent one is actually one that I don't know if some of you had some kind of enlightened chemistry teachers at secondary school. If you did, you might have put some copper leads into some sulfuric acid and plugged everything onto the wall socket and then see what happens, in which case you might have constructed some copper sulfate crystals. Anybody do that? No, okay, you didn't have good chemistry teachers. Okay, so anyway, it's an extremely easy crystal to grow. So this can be quite a large chunk, a single crystal. It's very important that it's a single crystal. In this case here, it's a deuterated version, so that's a bit more difficult to get in your house. But anyway, to show how easy it is to construct, this artist in the UK actually did this in a whole apartment somewhere. I think it was back then in London, so he bathed the whole thing in sulfuric acid and plugged everything into the local mains outlet for a while, and then he grew copper sulfate on all surfaces of this apartment, which has many rooms, in fact, not just one. But I still have to check, I have to contact this guy and ask him whether he knows that these are one-dimensional Heisenberg magnets. So he might have realized the kind of largest concentration in the known universe of the Heisenberg models. But anyway, we'll see. So the point is that you can do some beautiful neutron scattering experiments on this model, and moreover, the measurements that you get, the experimental results that you get, are fit-free. So there's only one parameter in the Heisenberg model, that's the exchange parameter, and this exchange parameter can just be read off a high magnetic field measurement on this. And then essentially when you start comparing the curves for the response function coming from associated neutron scattering, it's a parameter-free fit. Okay, so the system is at very, very low temperatures. You can consider it essentially in its ground state. There is, of course, an experimental resolution to the response function because of the uncertainty in energy and momentum that you have. But modulo that, the fit should be perfect. And the nice thing is that the experimental accuracy is now sufficient to discriminate between the beta ansatz calculations and all other calculations that were known up to that point. Okay, so in the high energy region, which is precisely the region where other methods fail but beta ansatz stands firm, the fitting clearly shows that the best best interpretation of the data is obtained from doing the straight beta ansatz calculation. So this is really like beta wave functions in the lab that you have. Another crystal that shows similar results is KCUF3, so that's a crystal that's been known for a while, but it was restudied with more accurate experiments recently. So again, once again, the calculations of beta ansatz, they fit much better anything you can get from glorified field theory or other ansatz that were done here. Okay, so the message is that as far as experimental quantum magnetism is concerned, some of the best experimental predictions you actually get nowadays from beta ansatz. Okay, it's quite nice that you can see, at least for these cases, the capabilities of beta ansatz being reflected directly in these fits. Okay, so I don't know if any of you had seen some of these plots before, but it's quite nice. Okay, I have rather limited time, and essentially I want to now talk about a different, if you want, universe of physics. Question? No. I want to talk about a kind of completely different direction in which I think integrability should be going in the next few years. So the kind of arena is out of equilibrium physics. And let me just give you a little bit of motivation for doing that. I kind of like this because it's a nice illustration. Let's talk about the simple rigid pendulum. Many of you will know that if you take a rigid pendulum and just start oscillating its suspension point, then you will reach a sufficiently high frequency where the stability criterion will change. Okay, so if you drive it sufficiently fast, the pendulum will become stable in the upwards position rather than in the downwards position. Okay? So, how many of you knew that? Okay, good. You learned something today. So. Okay, so the remarkable thing is that this extremely simple thing could have been known by, Democritus or somebody thousands of years ago, but actually it was first described in, I think, 1908 in the literature, 1908 or 1909, and it was essentially clarified, or at least a theory for it, was only proposed in 1951. Okay, so you're talking about really simple classical physics here, but it took, Piotr Kapitsa to point this out, okay, or to calculate this. So this is an extremely nice example of separation of scales. Essentially, if you study renormalization, this is a good way of thinking about it. You've got a separation of scales of your modes, and essentially integrating out some high energy modes, you affect the low energy modes so much that you can just change them into something else. So this is what you get out of looking at this. And I was looking for some nice examples of this online, but then I found loads of big people with big machines. And I thought it can be simpler, so I tried to build one in Lego. So here's my Lego realization of the Kapitsa pendulum. It just oscillates. It's not perfect, but you see clearly that it's in equilibrium here. So this thing oscillates at about 20 hertz. My son was kind of screaming at me when he noticed that the Lego was really on the edge of its structural stability. It's just enough to get it to work. But that's the idea. So the reason why I want to use this as an illustration is because I think there's a lot of physics that can be obtained from considering out of equilibrium systems that are driven in particular ways. Okay, so you've probably seen many realizations of this. So you can imagine taking a many-body system and applying some time-dependent perturbation for a long time, and the system will equilibrate to some state, which is not an equilibrium state, but which is like a steady state, or a pseudo-steady state. Okay? And I think it's particularly interesting to look at this in the context of integrable models, because, once again, we don't care about the energy of the states that we write. It doesn't matter where we land in Hilbert space, we will have an exact description of these states as well. So beta ansatz and the theory of integrable models is, potentially the only way we can control truly out of equilibrium interacting many body systems. Okay, so I think this is really something that we're motivated to look at from the condensed matter side. And of course, it's not just theoretical stuff. in cold atom experiments, for example, they can construct such out of equilibrium situations that they can then go on and investigate. Many interesting questions that can be addressed. Okay, so there are quite a few things about out of equilibrium that you can do with integrability. Today I just want to very briefly talk to you about two recent, but I think extremely important developments concerning quantum quenches. So a quench is essentially a one-step chain. I guess I'll just describe that very, very quickly. Okay, quantum quenches, did you hear that keyword before, or were you kind of immune to, were you quenched by quenches? No. So what's a quantum quench? Essentially the idea is that you prepare the system in a certain state, and at t is equal to 0, you change the Hamiltonian. So for example, you might change the interaction parameter, you might change the anisotropy, you might change the geometry, you might whack it with something, okay? And then you let the system go and you see what happens. The point is, of course, that the initial state, being not an eigenstate of this time evolution operator here, this thing here generates a horrible mess, okay? And the question is, where does that lead you to? The things that you want to be able to describe are just time-dependent expectation values of physical observables, maybe local density correlations or things like that. Okay? And because the wave function here is an incredible mess, this thing here is also potentially quite a mess. You want to try to calculate stuff like that. Okay, so one of the big things that's been discussed in the literature is whether you can find some effective, simplified description for these things. And now you can go back to the old descriptions of equilibrium and statistical mechanics, even take out the old book of Josiah Willard Gibbs, and then you see how it happens. You've got some conserved charges, you introduce Lagrange multipliers associated with those, and then that gives you an ensemble of states over which you should sum to compute some expectation values. So the idea is that if you do such a quantum quench, then a long time after the quench, the kind of steady state that you should get should be essentially pinned by the dynamical constraints that are associated to the conserved charges that you have in your system. So if your system is just say a three-dimensional non-integrable model, you again just have energy conservation, particle number conservation, and then you should thermalize. So you should just go to a finite temperature state. However, if you're in one dimension, of course, you've got many, many different conserved charges, and these might constrain your dynamics such that if you perform a quench in 1D and you wait long enough, you will get a state which is not thermalized. Okay? And it will never thermalize. Okay? Surprisingly. So that's the kind of framework that you want to investigate. So the way you would describe such a state is using a construction that's now become known as the GGE, the Generalized Gibbs Ensemble. Any of you heard about GGE before? No? Okay. So the idea of the GGE is extremely simple because you just generalize Gibbs's logic by introducing all the conserved charges that you have here. Okay, so for example, if you were to do this in XXZ, you would just introduce all the charges that you would get from the trace identities associated with the transfer matrix. And then you see what you get. Of course, then the idea is that you would read off these parameters here, these effective temperatures for these charges, from the initial values of these. These are conserved charges, therefore the expectation value at t is equal to 0 is equal to their expectation value at t is infinity. Okay, so they represent constraints. So you'd have a system of equations essentially constraining the possible values of these parameters, and then solving these equations, so the initial state would determine these things, and therefore these things, you would get a density matrix that would allow you to compute everything in the steady state. Okay, so that's the thing. In reality, of course, this is very difficult to implement because the charges are generically non-trivial if your system is interacting, and the self-consistency problem you have here might be very, very difficult to solve. So in practice, there have been hundreds of papers where this has been looked at, but typically it's just for free theories. Okay, so one of the challenges that I wanted to address was how this works for truly interacting theories. Okay? So in the case of true interactions, it's not understood. So let me just very briefly tell you about two examples that we've been able to solve. So Lieb-Liniger, okay? Seen that, beta-ansatz correlations, know that? Now, what we're going to do is that we are going to prepare the Lieb-Liniger gas in the ground state of the non-interacting system. Okay, so it's a state which is completely, where all the particles live at zero momentum. So the momentum distribution function is just one massive delta peak at k is equal to 0. And then, at t is equal to 0, we will turn on repulsive interactions. Okay? So, of course, before t is equal to 0, the particle positions are completely uncorrelated, except for the bosonic statistics. But from t is equal to 0 onwards, when you turn on the repulsive interactions, if two particles happen to be close to each other, they will explode away from each other. So the momentum distribution is going to broaden. You're going to heat up the system quite substantially, and the question is, what happens here? Okay, so it's a tough problem to treat. This has a long history with many attempts and failed attempts, and then various things. Let me spare you all of this. If you're interested, I'll be very happy to show you all this in private. But it was the first circumstance in which a new approach that I devised with my collaborators, Fabio Vesta, a little while ago, actually bore its fruit. So this I like to call the quench action approach. Let me just very briefly explain to you what the point of that approach is, because it's very, very close to the thinking that you use when you do thermodynamic beta-ansatz. Okay, the idea is that when you want to describe a quench, you've got some initial state, which might be an eigenstate of some Hamiltonian. And then you want to describe the time evolution of that quantum state in the basis of eigenstates of a different Hamiltonian. So the very same quantum state, that is here, just this single point, is described as kind of a splash of wave function amplitude in the basis of eigenstates of this Hamiltonian here. It's the very same quantum state. So now what's going to happen, of course, is that all the states here, living at different energies, will start oscillating at their own frequencies. So there's going to be a massive dephasing occurring in the unitary time evolution of this quantum state. Okay? So the idea of the quench action is just to say that you represent this splash of amplitude as a pseudo-free energy functional. Okay, so you essentially, I'll show you the equations maybe later, but you define a new pseudo-free energy which is given to you by the overlap of the initial state with the beta state that you're considering, modulo the entropy, and you can write this, this pseudo-free energy so that it is bounded from below, it has a well-defined minimum, and then you can do a saddle point evaluation of these things that looks very much like a thermodynamic beta-ansatz, that gives you the steady state a long time after the quench. Okay? And the approach to the steady state, the relaxation processes, are just completely described by looking at the vicinity of this saddle point. Okay? So that's just kind of the philosophy behind it. In equations, I'll just take 1 minute to do this. The idea is that you project the initial state onto the state of exact eigenstates that you have, modulo the overlap amplitude, so these things here are just the logs of the overlaps. Okay? And then you replace this sum here by a functional integral, like we've done for thermodynamic beta-ansatz. So the time evolution of the observables that you have can be written as this double Hilbert space sum, and then this is intractable, but under a saddle point evaluation, you can just do it. Okay, so maybe I can refer to you. I mean, just look at my recent papers on this. You'll see the explanations. The idea is that the overlaps of the initial state with the initial state give you a new pseudo. Instead of the Gibbs free energy, this is a new form of free energy that encompasses the information from the overlaps. And then the saddle point evaluation of this is just like you've done for the TBA. So you've got some saddle point condition which gives you a root distribution which characterizes the steady state. Okay? So it's just that. And this is just showing you how you can then calculate the expectation values of these things. Let me run over those details for now. Okay, so the important thing is that the full time dependence of these expectation values, you've kind of boiled down to some very, very simple data that you can read off. from these formulas. Okay, so yeah, details here. Okay, so the point is that the application of this method requires you to be able to calculate the exact overlaps between your initial state and your beta states. Okay, so then the problem goes back to mathematics now. So one of the things that we came across last year was that if we look at the this initial state, which is a Bose-Einstein condensate-like state, so everybody in the zero momentum state, we were able to find an exact formula for the overlap of this state with a generic beta state. So this is like a kind of different take on the Godin formula. It's like a doubling of a Godin formula for the number of states, but this overlap here is exact. Okay, so we thought it was an isolated case. These exact overlaps are given once again by determinants of matrices whose entries are explicit functions of the rapidities we have in the eigenstates. Okay, so then, knowing that, we could just apply this quench action approach, and then the final result is that we obtain a closed form solution for the steady state after this quench. And these curves here are the curves representing rho of lambda, so the density of roots of the beta state being representative of the steady state. Okay, and you can so we've shown that it's non-thermal, etc., etc. Okay, so I'll refer to you to the paper for this, but one of the extremely important statements from this work is that the GGE construction could not be implemented here. Right, so we got the exact solution with the quench action, but the GGE made no sense. Essentially, all the conserved charges were infinity, but so it was kind of the first example of a failure of GGE. Now, very recently, the same thing has been done for a different quench now in quantum magnets. So here the idea is that we start from a pure Néel state at t is equal to 0. So this is an eigenstate of the E-sig model. Okay, delta is infinity. And then we quench to xxz. Okay, we quench to this Hamiltonian. Then we see what happens. Okay, so once again here to treat this problem exactly, we need the exact overlaps between the Néel state and the beta ansatz eigenstates. And here, of course, the business is quite non-trivial because the particle content, the content of spin chains is very complex. So you have to be careful how you solve all these things. But as far as the overlaps are concerned, based on earlier work by Tsuchiya, others, Kozlowski, Poskai, we came up with another form that is also some generalized Godin determinant, or some Godin-like determinant for these things. So once again, this is an exact many-body wave function overlap that allows you to compute the effective quench action and then do the generalized TBA to get what the steady state is. Let me just show this to you in like 10 seconds because that's what I have. Okay, and then the statement is that, let me just refer to the literature for this. The statement I want to make is that this exact solution is in disagreement with calculations based on a GGE, where the GGE contains all the known local charges. Okay, so somehow, just having the dynamical constraints coming from the local charges is insufficient to point you to the correct steady state. And this has, of course, an influence on the distributions you get in the steady state, but also on any measurable correlation function. Any correlation function will show the difference between the two. And even it's possible to do some numerical checks on this and point that the quench action solution gives you the correct expectation for these things instead of GG. Okay, so in a sense, so also the group in Budapest got some results on this. So they reobtained our Néel results. They also considered a different quench to a dimer state. They got some numerical evidence for this. So there remains little doubt about these statements that the quench action gives you the correct result, but the GGE fails to converge. And essentially, there's a lot of discussion now in the community about explanations for this mismatch. So essentially, the statement is that there are probably important non-local conserved charges that do affect the physics of these models that we've never talked about, that we've never considered because they were just, not really directly related to physics, but these quenches might be enough to reveal them. Okay, so this is where we are at the very moment. Okay, so there are some proposals to repair the GGE. In a sense, when you do the GGE with all the dim Hilbert space conserved charges, it has to be equal to the quench action. Question is, what's missing? Right? So that's essentially where we are at the very moment. I'll be very happy to discuss these issues with you in private in more detail if you want. Okay, so in summary, I think from the side of condensed matter, the number of applications of integrability has really exploded quite substantially over the last few years. And I think that this new arena of out-of-equilibrium physics is going to be an even better setting in which integrability can be used to investigate some physics. And I think these questions of locality versus non-locality are potentially extremely instructive for the whole of physics. So yeah, I'm sorry it was kind of a lot of stuff. I was given 4 hours and I essentially put content for about 20 hours of these 4 hours, so I apologize for that. However, I'll just tell you that if you have questions about all of these things, I'll be happy to answer them either now live or by email at any point in the future. So, thank you very much for your attention.